Good morning and welcome to a review of the HTG Molecular's EdgeSeq Review of Reveal. Reveal is a new pipeline software package that we are offering our customers who work with HTG products that enable them to be able to literally do data analysis at their benchtop or at their laptop. This is a great tool from the standpoint of as soon as you receive your data back from the parser and upload it into Reveal, you can begin to look at things like differential expression. You can do your own quality control and a whole host of other things that we're going to review this morning. I'm showing you right now what is the quick start guide, and this is a guide that you can get from both your sales representative or from your technical support folks that you're working with regards to the HTG products. In this start guide, it's actually going to walk you through pretty much what I'm going to show you today. It's just going to be in words and in pictures. And so we will today cover log on, and we'll talk about what the process is to be able to log on to the Reveal software, how you actually load a parsed data file, as well as an annotated data file, and it's going to be really important that you pay particular attention as to how to build out that annotation file so that it works flawlessly within the Reveal system. What we're doing when we actually perform QC, how to use our PCA or principal component analysis, a great high-level look, right, at what the different groups of patient cohorts are doing, if you will, within a given assay from a high level, as well as, how that plugs into our current precision immunooncology assay. There's also a series of help tools which I'll show you online, so you don't have to go someplace else on your computer or through your email to find those help notes and technical files. The other thing I'll also mention is that though we'll focus today on the precision immuno-oncology assay, in June we will be launching an update to our Reveal software, which will enable you to look at the same types of tools for our oncology biomarker panel or OBP panel, as well as our new mouse mRNA tumor response panel. And so we're going to follow a very similar format to that. I would encourage you as a customer, as you are looking through and working with this software, that if you think there are tools and additional features that HTG should add to this particular software and pipeline package, that you provide that feedback so that we can make sure that we're providing you with the best possible tools going forward. So I'll roll through this just very briefly, but this is kind of showing you at a very high level and pictorial level, the way that we QC, the fact that we do some normalization and analysis with PCA, and then on to the visualization, if you will, or the development of gene signatures through differential expression analysis using two groups. You can see you can get a variety of different outputs for that. So I think probably the best way to really demonstrate this is to truly just demonstrate the actual software itself. So when a customer becomes, or when you become interested in working with the pipeline, you contact your sales representative or your technical support team, and you tell them that you're now ready to do analysis on your of the product on the actual Reveal pipeline. They will then provide the necessary information internally to HTG that will enable you to get access to this software. And it will come to you in the form of an email that will give you some instructions on how to actually log in. Once you log in, it will go through an authorization process, which you see it doing right now on the screen. That doesn't take very long. And then it will give you some information about what Reveal is, right, about what the actual hosting software is. It'll also give you some information on kinds of the terms of use, your consent, as well as the privacy policy. So one of the nice things about the software is that you're not really emailing your data anywhere or sending it across the internet. It's never stored, it's never saved. You're simply using the data on your computer and working with the bioinformatic tools associated with the pipeline. So it's a nice, safe, and secure way to be able to work with your data in this fashion. You simply accept the terms and agreement, and it's going to flash open to a screen that's going to enable you to do some data uploading. In the future, I believe this is going to have you select which assay you're actually uploading, whether it's precision immuno-oncology, whether it's immuno-oncology or the mouse mRNA tumor response panel. For right now, since there's a singular application in here, we're loading directly into our precision immuno-oncology assay. So you have the ability to actually load these data files on the computer at one at a time, or you can actually load several of them. And you simply increase the number by telling the software how many data files you're going to add, and that's being populated over here. Today, we're just going to work with one for simplicity, but you can actually add quite a few of them and tile them all together, which is nice, because if you're running data today and then you run data 3 months from now, you can actually combine those data files together and do the analysis work that you'd like to do. It makes it very simple. So we're going to load one data file. I'm going to go to Browse, and I'm going to select where my data file is stored. So I have a sample PIP data file right here. It's going to load it in, and it's going to tell you when that data file is complete. And it's also going to give you the information about what was just loaded. What was the sample name, what well was it run in, and what was the total read depth associated with each of those samples. I also have the opportunity at this point to add an annotation table. So an annotation table is very important because it's basically letting the pipeline know what are the actual two groups that you want to work with. So if we flip back real quick to your Reveal sample review guide here, let me go to, this is how you actually create that annotation table. And I'll tell you, it's been my experience up to this point in working with the software package that probably the hardest thing to do is make sure I've got my annotation table correctly. So you're going to actually load in your sample ID as it actually shows up on your spreadsheet back from HTG, and then you're going to denote which group. Now that could be, two different diseases. So in this case, we're looking at diffuse large B-cell lymphoma, annotated as DLBCL, and we're also going to be looking at some squamous cell head and neck tumors, which is the SCCHN. You can simply put in A and B, you can put in 1 and 2, so you can denote these in any way that you want to. But what's important is that the labels of sample ID and group, that they're written exactly this way so that the pipeline can identify what it is and then load it into the system correctly. And so once that annotation table has been developed, you can actually, same thing, go to your browser, find the annotation table that you want to load up, okay? And with the press of a button, you're now having fully uploaded everything. So you have both your data set as well as your annotation table fully loaded. From there, one of the very first things that we do is we go through a quality control process. So I simply hit the quality control tab here, and I'm going to have several tabs that show up to the right, if you will, of the main gray box. The gray box is an export, so you can export raw data, CPM standardized data, median normalized data, and quantile normalized data. All of these plots also associated with RQC can be downloaded. And so I'm going to walk through that in just a second. Now, the one thing I also want to point out at this point is that sometimes this can get a little confusing, especially when you're first working with it. And so you simply can go over to the Help tab and actually check on, if you will, or click on the Quality Control tab, and that's going to give you the information about what each of the quality control measures are, from 0, 1, 2, and 3, and then some data associated with how those cut points and set points were actually developed and loaded into the system. So again, this is at your fingertips for every single tab that we have, and you can stop in the middle, go look, and then come back, and it won't disrupt anything that you're working on. So I look at my QC0 plot. This QC0 plot is basically letting me know that I have enough sample in the assay to be working with the assay appropriately and delivering good data. And you can see that black dots actually represent that the the sample load was appropriate. If for some reason the sample load were light or shy, what it needed, it would show up as a red dot, and you know that. This table can be downloaded, right? So it's going to come out as a JPEG file, and you can actually save these and rename these and use these as figures, right, in posters and in presentations and in papers. QC0 plot, this is a second QC step that we go through. QC1 actually is now telling me, hey, did I have enough read depth? So each one of the assays, we've worked through a process where we've looked at what the maximum or minimum amount of read depth is required to give good and robust and reproducible data. If you don't have read depth that's high enough, again, just like the nomenclature from QC0, black dots mean I have a high enough read depth, red dot mean I probably didn't read deep enough. And so for that reason, this might be data that you might want to eliminate from your data analysis going forward for that reason. Again, same feature of downloading the plot, where you're able to actually then capture that picture or that image, right, and use it in a report or a format later on. In the QC2 plot, this is where we're looking to make sure that the S1 is functioning appropriately, and we do that by making sure that there's enough differential expression across the genes in a given sample to tell us that S1 doesn't, did its job and that we don't have spurious probes coming through the assay. And so you would expect kind of this scatter plot, if you will, and you would expect standard deviations, right, to actually be high. That's what you want in this assay. When the standard deviations are low, meaning everything is the same, right, that tells me that S1 isn't working. So in this case, we actually have a nice, robust system that's going on from a QC2 standpoint. All of the samples actually, passed. You can see anything that would have fallen below this line here at the 0.15, that would be telling me that there wasn't enough difference gene to gene within a given sample. And again, downloading is possible. Now, if you don't want to save these as plots, you can certainly also download a table. And so the table is going to go through by sample, right? What was the percent pods and did it pass? What was the total count and did it pass? And then what was our standard deviation and did it pass? And it'll give you an end result of, did I pass all three for each sample? And if I did have a failure, where was that failure? Okay. Once this is complete, you have the ability to then go through and check these boxes, tell it what data you actually want exported, and then I can download those results much in the same way that we downloaded the figures associated with the plot. Once that's downloaded, you simply click on that. It's bouncing. Yep. It just takes it a while. And voila, you now have your Excel spreadsheet. So on your Excel spreadsheet, and again, you can rename this and save this how you like, it's going to show you the raw data. Raw data is going to give you those sample numbers. It's going to give you information about the run, the when, the why, the how, the versions. It's also going to give you the read depth, and then it's going to show you the data associated with positive and negative controls, as well as the genes of interest. It's going to show you what the data is from a QC raw. So basically, if you have a sample that failed QC0, QC1, or QC2, that data is then omitted from the QC raw because there's thought to be or felt to be a flaw associated with that data. Now, if for some reason you look at the data and you say, you know what, it was pretty close, I think I'm going to count it anyway, you can always go back to the raw data. The raw data is still there, right? It didn't erase the data. It's just we're not going to carry it through on our pipeline going forward, but you always have access to that data. The other thing is that for data integrity reasons, we really only want to touch that raw data one time, right? And we touch that raw data one time when we go through the QC step itself. And then from here on out, we're always going to be using the QC raw data. That maintains your original, native raw data file intact. From there, you can see your CPM, right, which is your counts per million. So those that are familiar with sequencing data, where you're doing sequencing data that reads things in counts or reads per million. The counts per million is simply our terminology because we're counting capture probes rather than reading sequences necessarily. Median normalized data, and then also the quantile normalized data. So, and you notice in every one of these, column M is missing, and that's because there was a failure at the QC step. Okay. From here, we can then begin to move into correlations. So the nice thing about correlations, right, is that they're both positive and they're negative correlations. So at HTG, when we actually run samples, every assay that we run, we put in controls. And we run those in triplicate, and it's just a measure for us to make sure that the assay works correctly. You can also do that within replicates of samples, right? So if I actually go in here and I pick, you know, a couple of my head and necks, or I pick a couple of my DLBCL samples, I can look at those and understand what the correlation is from both a Pearson and a Spearman correlation. So let me go in and I'll click my squamous cell 2s. And there's another one down here, squamous cell 2. Boom. Okay, so I picked 3 of those. I click calculate. You can do this with controls. You can do this with replicate samples. And I actually can see that my Pearson and Spearman across this biological replicate is 0.99 and 1 for my Spearman. Again, just like all the other assays and things that we run through this pipeline, you can actually click on it, download it, and again, save it in a format that allows you to publish it later. A lot of people think of correlation as, hey, I want to prove that the correlation is a good correlation, right, and that everything is correlating. But sometimes it's equally as important to understand, hey, if I threw something in the mix that wasn't quite right, would I actually see it not correlate? And in fact, you do. So in this case right now, I've got the 3 head and neck tumors. I threw in a DLBCL, and not surprising, my head and neck tumors continue to correlate, but my DLBCL doesn't. And you would expect that, right? So again, it's a way for you to check correlation basically in both directions. The next thing that we'll talk about is PCA. With PCA analysis, I really like this feature because it allows me to look at a very high level. Are my groups actually clustering and giving me different types of gene expression analysis? Now, with 2 disease state types, it's probably not surprising that you actually see these cluster very, very far apart. And that's not to say that if you have, you know, pre and post tumors that you're analyzing, or you have stage 1 and stage 2 tumors, and those dots, if you will, are sitting right on top of each other. It's not to say that you won't see statistical significance on some genes. It's just saying, hey, those populations are just not that different from each other. And so I think it does help manage the expectation of what it is you might actually see as you do further analysis. Now, you do have the ability, this is kind of a default setting, and you can tell, you know, most of my DLBCLs are sitting, you know, to the left, the others are sitting to the right for my head and neck tumors. And then down here you have a little overlap. So again, the nice thing as a user is that you have the ability to continue on with the analysis, knowing that you do have these handful of samples that are overlapping. But the other thing that you have is the ability to roll over the top of these, find out what samples these are, and see if there is something about those samples that could be causing this phenomenon that you're seeing. And then you can make an informed decision as to whether you want to include or exclude those from your analysis going forward. So you get that info. On the X and Y axis, you can actually look at this in a variety of ways. This axis will move around, and there are some guidelines inside the PCA help to kind of talk about the scaling and the parameters and how you might use those. I personally like to look at these as the 1 and 2, at least initially, and then start to look at scaling when I'm asking very specific questions. I also have the ability to look at the PCA just based on the genes themselves. So you have a total look at the PCA, but you also have the ability to select some genes and some gene sets. So if I want to look at, hey, you know, what's the PCA associated with these genes and how do my samples actually cluster, you can see you begin to get very, very different clustering as a result of that. So Nice thing is you have manual, which is everything, or you have set, which is everything, and you have manual ability, which can look at very specific genes. And then the last thing that we'll talk about, actually I'm going to go back to this. I'm going to go back to my original format and move on to the differential expression analysis. So the differential expression analysis that we use is a two-group differential expression analysis. So based on, again, the way that you have written the annotation table up, that will determine the groups, if you will, of samples that will be analyzed one against the other. You do have the ability to do manual entry, though I have to tell you, doing the annotation table is a little bit faster. And it also allows you can build multiple annotation tables so that you can look at the data very differently. And that's also quite helpful. So you click the modeling parameters. And this is going to basically allow you to select, hey, which is my reference group? Is it DLBCL or is it head and neck? And then it'll give you three different testing modalities. So there's LIMA, there's EdgeR, and there's DESeq2. Now, we actually have kind of a debate heavily, with our biostats people all the time about what one of these testing modalities is best. It does appear as though in the literature that the DESeq2 does seem to be the one most commonly used with sequencing data. And so that is the default that we do use. There is a fair number of folks that are very used to using the EdgeR, and so we allow that, obviously, the opportunity to be able to use that, as well as they're very familiar with LIMA. Again, if you want additional information on the differential expression, being able to understand kind of why you might select one over the other, there is the help desk here that allows you to understand what those different software packages are offering you, as well as documentation and references that you can go look at to further educate yourself if that becomes something of interest. So by selecting the DESeq2 parameters, you can actually go through and do the modeling. So if I hit perform, and I can tell you, looking at differential expression between DESeq2 and EdgeR, it will give you different results because it's actually approaching the data a little bit differently. But surprisingly enough, more times than not, those genes that are overexpressed or upregulated with one tend to be upregulated with the other. They might be in a different sequence in terms of highest to lowest, but they tend to be upregulated, and the converse is true with the downregulated genes. Now, the first thing that you'll notice is that you will get a table, and again, this is exportable. You can see you can export the tables and all of the different plots associated with what we're getting ready to do, and there's a little selection menu right here. The table basically is telling you, hey, what's the mean of all of my head and neck tumors for that gene? What's the mean for all my DLBCL tumors for that gene? What are my averages? What's my fold change? What's my raw p-value versus my adjusted p-value with FDR? And again, this all can pop out into a spreadsheet format by simply downloading, just like we've done with the other data, the DESeq results. And when you open this up, right, it's going to give you the differential expression analysis. So it'll also give you some definition about what these headers actually mean so that you know exactly what's happening on your spreadsheet when you look at that. The next thing we can do is a volcano plot. So again, nice pictures for publications and for posters. It is a way for you to visualize what are my up and down regulated genes. If for you, the thing that you're most interested in is, hey, I want to know what's happening. Let's do this one. I want to know what's happening on the top overexpressed genes. You can literally kind of pull this plateau down, right, off the plateau ridge, so that you can actually see where those genes are falling that are up and down regulated. If you are really interested, hey, I'm kind of more interested in my low abundant genes, you can actually flip this the other way, right, and get yourself some better definition on the genes that are lower expressed. Okay. Let me turn this back to default. The second thing that the software will do is it will give you some up and down regulated box and whiskers plots. The one thing that I will caution you on when you look at these plots is that both the up and down regulated gene has their own plotting feature, meaning that the actual scale, if you will, of each plot will solely rely on the level of up and down regulation associated with those genes. So it's possible that I'll have 5 logs on one scale and 2.5 on another. And so magnitude of change sometimes can be a little tricky to evaluate visually if you're not paying attention in particular, right, to those scales. So that's the only thing I'll warn you about. In this particular case, you actually see we're on a 5-log scale. And so differential expression, right, between these two disease types for this first gene is actually quite large, right, because you're almost 10 logs from the median. You have the ability here to actually increase the number of genes that you see on the plot. I can tell you once you start getting up above 20, it gets pretty onerous to look at because it's just so small. But remember, you do have the ability to go in here and actually download this plot. Right, and you can stretch that plot out, and then you can actually really see what might look pretty small online can actually look pretty easy to look at. I'd also tell you to pay particular attention to what the title is at the top. So these are the top 20 significant upregulated genes. When you're working in small sample sizes, right, and you don't actually have true significance, you might wind up trending towards significance, and in that case, the title of this might be, you know, top 20 non-significant upregulated genes. And it's really just giving you the ability to see your trending data versus your true statistically significant data. So again, things to watch out for. Title, you know, what is the data actually telling you, along with what are the actual spacing, if you will, or scaling of your actual logs. From here, we can go into heat mapping. So again, depending on what you're interested in looking at, you can go in and create and look at pathways that have already been created. So, you know, we can go in and say, okay, between these two, we really want to look at epithelial, the EMT. And I want to cluster this by probes. So create my heat map. I'm going to open this up a little bit larger. Over in the corner here, it has the download plot. So I can click on that, and this new plot will be downloaded. I really like using that feature as a way to actually look at the data, and it's basically giving you hierarchical clustering based on the genes. Now, I could just as easily go back into that and say, you know what, I don't want to cluster on genes. I want to actually cluster on samples. And again, I can go back over here and download. So really simple. It's what do I want to know? What's the question I'm asking? And now I'm clustering according to genes. And remember, right, we had big clusters that were fully segregated between the DLBCL and the head and neck, and then we had some that were slightly overlapping. And I think you'll find that that's basically representative of what we're seeing in the heat map. You also have the ability to make your own genes. So let's say you have your favorite genes and you want to do some manual entry on your favorite genes. You can go through, whoops, wrong thing, sorry. You can go through and select your genes that you're interested in, creating your heat map on. You can also go in here and search. So if I click off, you know, A2M, right, it'll show me that one and I can click on that. I can actually do just what I did before, and that is to go in and build my heat map, and I'm going to get exactly the same, you know, kind of thing that I looked at before. I can download it, and again, through downloading, I can get a really good visual on the hierarchical clustering based on the genes that I'm interested in. Okay. As I mentioned before, all of the tabs that we have with all of the different features that are inside of the software, they're all going to have information regarding exactly what it is we're doing, why we're doing it the way we're doing it. There are multiple downloads. There are also some tech notes in here. So for folks that are interested in things like tumor inflammation or the EMT, you can go in and you can download these. And this will give you, hey, this is exactly what the gene set is that we're looking at. You know, this is some of the data that was generated internally to support this cluster and segregation of the genes, and a little bit of information about the technology. If you have further questions or need some additional help, we're happy to hold personalized